Boom. Hello and welcome back to Calculus 1. I know, right? Finally, we can start talking about the calculus. We said that there are three parts to calculus: limits, derivatives, and integrals. And the first one that we are going to talk about is the concept of the limit. The funny thing is that the limit was precisely defined the last. So Newton and Leibniz figured out differential calculus without knowledge of the limit. They just used the notion of the very small, right? And then also Newton, Leibniz, and then Riemann and so on worked on integral calculus. And then Weierstrass in 1850s put the definition, which in our textbook is all the way in 2.7. So the pure math definition of the limit is in 2.7, and we're going to see that. But now, what we want to do in the section on intro to limits is we want to get the feel of what the limit is and what it represents, how to find the limit and its basic form. And then we're going to have cool techniques and everything else in 2.3 and later. So, in the nutshell, the most important sentence over here probably is: limits compute y values of functions. And that's it. So, limits compute y values of functions. Now you're going to say, well, wait, wasn't that what we did in pre-calc? When I say f of 3 is equal to, you plug 3? Yeah, but the limit does it differently, which gives it so much power. So let's take a look. You have your good old function that you all know and like. F of x equals, say, x squared. The pre-calculus will ask you what is the f of 2, and you will say, it's 2 squared, it's 4. Great. The way to show that in pre-calculus on the graph you will have the graph for x squared. You will go at 2. We will go up until you hit the line and bounce to y-axis and read that the answer is 4, claiming that this point is 2, 4. So, you went straight up from 2 until you hit the line, and it bounced you off to y, and you read the value. And that's the reason why f of 2 is 4. X squared, 2 squared, 2 times 2 is 4. All right, time to do some calculus. What is the limit of x squared as x goes to 2? It's 4, right? And at this point you would say, so why, right? Why do we do this and what it means, right? Why have another way to do the same thing? Well, I just need to draw x squared. There we go. All right. So now we still have the same image, but we are going to compute the value in a completely different way. First off, I'm going to call your attention to one of the most important concepts in calculus, and that is motion. Calculus studies motion, and the motion in limit is captured in this x goes to 2. x approaches 2. Clearly, if you want to approach the desk, you will walk to it, right? So there are 2 ways for me to approach 2. I can approach 2 from the left, and I can approach 2 from the right. That better be clear, right? So now, observe what's happening with y values as I am approaching 2 from the left. Pick this point here. Go up, it's that point. This point, there. This point, there. Do you see that as I go to the right, I am actually climbing up, which is climbing up over here. Do we see that? I'll draw this one, that one. Do we see that? It's a progression. It's not a single calculation. You are computing infinitely many points as you are approaching 2. You are at 1.5. What's my y value? You are at 1.6. What's my y value? You are at 1.7. What's my y value? You are at 1.73, right? So there are infinitely many points in front of 2. And you are going through each single one of them, and you are observing the trend of this point on y, the answer climbing up towards 4. As you are doing the same thing from the blue side, from the right, you are starting all the way up, and these guys progress down. And you see that the red and the blue are going to collide at 4. The calculation that limit provides and the calculation that the pre-calculus provides are completely opposite of each other. Pre-calculus doesn't care about any other point in the galaxy other than the point 2. You plug the 2, 2 squared is 4. It doesn't care about 1.9. It doesn't care about 2.11 or anything else. It is 2 that is squared. It produced the 4, and pre-calculus is done. Calculus calculation doesn't care about 2. It cares about all of the infinity of the red points in front and all of the infinity of the blue points after. And it's going to look at the trend, at the progression of the y values, and infer the answer at 2. With limits, you never compute at the point of interest. So what's the big deal? It's a huge deal. Let's say a section of a bridge falls off, breaks. How do you fix it? You approach from one side of the bridge with materials and machine and people, right? And you approach from the other side of the bridge with material, right? And then you work on fixing the issue in the middle. That's the limit idea, all right? What would the pre-calculus fix the bridge be? The analogy. The magician goes there and goes, poof, it's done, right? Teleporting at the place where there is nothing and that section of the bridge and just poof. Because you're not allowed to bring materials from any of the sides, right? This is natural, right? This is the way we operate, we work. You have to cover all of the infinity of the points to approach that door, right? That is what the motion means, right? Go from point A to point B. There are paradoxes and other cool things, but in this case, we are not computing at 2. We are going to look at the trend, this trend, and we are going to conclude from the trend that the value we are going to is 4, and we call that a result. Now let's do that in a chart. Let's do that in a chart. So our job is to figure out what is happening with the y values. So these are your x values and these are your y values. Your job is to calculate the limit of the function at 2. You are not allowed to calculate 2 exactly. We'll see the benefits of that later. So instead of calculating at 2, you are going to go to 1.9, like $1.90. Then you are going to go into $1.99, which is closer to 2, right? You would all agree that $1.99 is closer to $2 than $1.90. And then you're going to go to the gas station where you're going to have 3 nines, right? When you go to the gas station, that 9 over 10, that's this third 9 over here. Oh, please make sure you ask for change next time there. They calculate the money on the third decimal. And then we have the 2.1, that's $2.10, $2.01, and $2 and so 0.001. All right, time to get the abacus, do some calculations. 1.9 squared is, I'm going to, guys, I'm going to use the red now because this is the red approach. 3.61. 1.99 squared is 3.96. 1.999 squared is 3.996. From 3.6 to 3.9 to 3.99, where is it going? Is it going to 18?
4.
No, it's going to 4, right? Because you see that these decimals are inching towards 4. Bueno, 2.1 squared is 4.41 on blue side. 2.01 squared is 4.04. And then 2.001 squared is 4.004. So what are the blue ones doing? Yep, they're going down to 4. If it walks like a duck, and it quacks like a duck, it's a duck. So it has to be 4. Right? And if you find this extremely simple and so on, I'm sorry, but that's it. All right? So instead of computing values directly, we are going to look at the trend of all y values and say, where are these going? And clearly in this case, the red ones from 361 to 396 to 3996 are clearly going to 4. These guys, 441, 404, 4004, are clearly falling into 4 from both ends. I call this Romeo and Juliet approach, right? The red and blue. All right? And then they end up at the same spot, or they don't end up at the same spot, which means there is no limit. and we can have that, we have plenty of time, we can have that calculation as well. So let's take a look at the situation when there is no limit. Limit of 1 over x as x goes to 0. Great. We better know the graph, right? It's a basic graph. So I am supposed to approach 0 from the left. That's the Juliet red. And boo for the boys, right? Romeo from the right. So now as they approach, they're not going to meet. Hopefully you see that as red arrow approaches, it is going this way, which goes towards negative infinity. What is the blue one doing? Going up the line to positive infinity. And they don't get to meet. Right? Now we can see this in the chart of values, just like we did for the previous example. I'm going to have my 0 in the middle, x and y values, right? And then I'm going to, oh come on, approach from the left and from the right. Approach from the left is going to be negative 0.1, negative 0.01, and negative 0.001. Again, you are 10 cents away, you are 1 cent away, you are 1/10 of a cent away. From the right-hand side, 0.1 all the way to the right, get closer by being 1 cent away, and then finally 1/10 of a cent away. Now, for our red calculations, negative 0.1, so 1 over that is negative 10. Then negative 100, then negative 1,000. Next one is negative 10,000, 100,000, negative million, negative 10 million, negative 100 million, right? So hopefully you see that this trend goes to negative infinity. As you are approaching from the blue side, you get 10, 100, 1,000, and this trend is positive infinity. On the one-dimensional plane, negative infinity and positive infinity do not go the same way. So, no limit. They don't get to meet at the same point in space. One goes to positive infinity, one goes to negative infinity. There are other examples we're going to cover next class with step functions. Let's say taxes are step functions. Piecewise functions as well, they have these concepts. So there are other ways for us to understand all of this material as we go along. I will see you all in 5 days. Do insane amount of homework. Oh, by the way, 2.1 is 2.2 is not done because we still have to define the one-sided limits and so on. So you can at least start the homework with a little bit of understanding, but we'll finish all of this. So the goal for next class, finish 2.2, 2.3, 2.4. See you all in 5 days.